Hello, I'm Deborah Byrd. You're watching EarthSky's Sun News of the Week, and our friend Dr. C. Alex Young is back with us today. Hi, Alex.
Hey, how are you?
Good. Alex is a heliophysicist. Oops, hang on. I had the YouTube tab open too. Alex is a heliophysicist, and which is a scientist who studies the sun, and he is at NASA Goddard Spaceflight Center. So, Alex, welcome.
Thanks. It's good to be back. I've been away for a while.
You were in Chile, right?
Yeah, I was down there looking at not our sun so much, but other stars in the southern sky.
Those other suns.
That's right.
Those other suns. So, which did you go to a big observatory?
I did. I went to the uh, Vera Rubin, which is
Nice, brand
used to be
new.
the survey telescope was renamed Vera Rubin.
Oh, I
That
see.
that is going to be online probably within the next. Well, it's actually they're actually testing right now, so we
How
should be getting
cool.
data within about a year.
Wow.
Unfortunately, I didn't get to see any images yet. They're all still secret, but I was on the plane with some of the scientists, one of whom I actually have a book of his, so it was pretty cool. I got his autograph.
Aw. That's cool. Well, I was just going to say that I was a big fan of Vera Rubin. She was so kind to me when I was starting to be an astronomy writer 50
Uh-huh.
years ago. And she was a very respected and revered astronomer even at that time. So
That's
she had
cool.
Vera Rubin discovered that she made a pivotal discovery related to dark matter.
That's
So
right. That's right. Due to the rotation curve of galaxies, very very cool stuff. So yeah, I it was quite amazing. I mean, the telescope itself is huge. It's up very high. It's not as high as Mauna Kea, but definitely the sun itself was very bright. You have to make sure you have really good sunglasses with UV protection and wear lots of sunscreen. But we went inside and got to see the whole building, which is massive. There's a multiple buildings. There's one that's just the assembly repair building where they recover the mirrors, and then we went into the actual telescope, and that is just completely blew my mind. It's just amazing. It's so huge. I mean, when it finally goes online, it's going to be able to produce images of the quality of Hubble.
wow,
Yeah,
that's
it's
wild.
it's pretty spectacular. I'm not a nighttime astronomer, but boy, I've been looking at the stars since I was a kid. Had my first telescope as a kid, so it was quite a treat.
Wow, that sounds fantastic. Yeah, there's all a lot of observatories in northern Chile. Was it northern? Is it in northern Chile?
Yes, ma'am. And I actually did go to another set. I went to the Magellan telescopes. They're twin telescopes. Those are actually online. So I saw the Magellan telescopes. Now that was cool because they were able to turn the mirrors down so I could look directly into the mirrors. That was pretty fantastic. Yeah, Atacama Desert. Thanks to the geography with the Andes Mountains and the coastal mountain range, uh, means that it's incredibly dry. It's the driest desert on the planet. Right now, they have 50% of the major observing telescopes, but as soon as Vera Rubin and the Giant Magellan and some of these other ones come online, it will then have 70% of the major observing in the world. And
Wow.
there are a huge number of telescopes. I didn't see it up close, but I saw the Gemini South. So in Mauna Kea is Gemini North. And there are telescopes that are run by the European Southern Observatory, the National Science Foundation, and Japan. There's some other ones. And also, I didn't see the telescope because it's up too high, but I saw the base station for ALMA, which is the Atacama large millimeter array. It's the highest telescope. It's, I think, at something like 17,000 feet. You have to,
Oh
you know,
my God.
you don't just hang out up there like the other
No.
telescopes. But it's, millimeter, which is microwave radio,
Right.
and it is able to just take these amazing images. I've seen um, an image taken from ALMA of a protoplanetary disk. So this is what happens before the star is born, before our sun is born. A disk of gas which is swirling around, and you can see the lanes where the planets are forming, and then the center is, of course, where the star is going to form. And it's such an amazing image. I remember seeing some scientists who work in that area say that when they first saw it, they thought it was a cartoon because the detail is amazing. I mean, you're looking at a solar system, which for optical, that's something we still haven't fully achieved. I mean, we have been able to see planets moving around larger stars, larger planets, and we're certainly close, but the detail is fantastic. It's such a cool image.
Is that image the one where this forming solar system looks like a spiral shape?
It's red. The image is red. It's kind of a, like like a record player. You see grooves around that are kind of,
I
it's not
see.
really a spiral, and then there's a bright patch in the middle, which is the star.
How
Um,
cool.
it's just, Alma's done some amazing work, and it's astronomy just continues to just blow my mind, and it's going to continue to do that.
Yeah, I mean, I've been doing this, like I say, for 50 years, and
Yeah.
it's never stopped amazing me. It's just gotten more and more amazing. So, speaking of amazing, let's look at this image, which is it's a composite image. This is not taken by a big telescope. This was taken from the ground by an amateur astronomer, Sunil Sandley. He gave us permission to show it here. And this is 31 days of sunspots for the month of October 2024. So just last month. And so are all of you watching out there, see if you notice anything about this image. And the thing to notice is that you can see that one big sunspot moving across the sun's northern hemisphere. But meanwhile, in the sun's southern hemisphere, there's many, 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 many more sunspots. And so we're going to come back to this image at the end of this show and talk about what's going on here. But we're just wondering if any of you have any guesses as to what's happening. And if you do, please put them into the chat. But now for the sun news of the week. So Alex, what's been going on the sun this week?
Yeah, so we of course have seen a lot of activity, which means a lot of solar flares, large ones, which often have associated with them CMEs, fast CMEs, which are, when they're directed towards us, can often be the ones that provide a lot more activity at Earth, aurora, and so on. But what we've seen this week is it's actually been a relatively quiet week. Now, and I say quiet only in terms of solar flares. So if folks will remember, solar flares they're rated in a scale that goes A, B, C, M, and X. And really the ones we care about are the M and X flares. The C flares are now kind of designated as common. The M flares we call moderate. The X flares we call extreme. And for those different ratings, each rating is 10 times the next higher one. So, I'm sorry, the one below it. So, for example, M is 10 times the C, and X is 10 times the M. Okay, and then you put a little number on the front of it, and that tells you it's 5M or 3M, for example. And this week, we've mostly just seen M1, so barely any M, very small M's, and for the last 3 days, I think it's only been one. So this is much different than seeing multiple M flares earlier in the week, and then over the past couple of months, we've seen a lot of X flares. So that we have determined is calling that low activity for now. But
And that's
really,
surprising because we're at solar maximum.
that's right.
Right?
That's right. So that's only part of the activity that we see, because one of the other things that happens during solar maximum is, we also have something called a filament or a prominence. Now, filaments and prominences actually turn out to be the exact same thing, but in the past, scientists thought they were different. When you look at the edge of the sun with space behind you, they appear as these sort of bright objects, and often we look at them in wavelengths that are red, or we look at them in wavelengths that we color red, and so that's a prominence. But it
So
turns out,
this
go ahead.
thing on this image, this thing that's to the left of the sun that looks like it's
Yeah.
spewing out of the sun, that's the prominence.
Well, you see this if you look in the back. So you see that bright fan structure. Okay, that is actually a sunspot. So those are that's bright emission coming out of the sunspot. But behind that, if you look very closely, you see what looks like a loop that comes out right sort of in the middle of the video. It's like a loop of rope has just kind of popped out. Okay. So that's the prominence.
Wow.
And prominences are really cool because if you've ever seen a total solar eclipse, or an image of a total solar eclipse, oftentimes you'll see right around the edge these pink or red structures. Those are in fact prominences. They do typically show up in eclipses in red visible light. That's a real color. And what you're seeing is material from lower down in the solar atmosphere that is supported higher up in the corona being the outer part that you see during an eclipse, the part where solar activity typically comes from. And they're held up by magnetic fields. And these magnetic fields not only hold them up, but restrain them. So it's sort of like they're tethered. And you could maybe think of it like a balloon with, strings over it that are kind of holding it there. And if those magnetic fields are disturbed, then that material can fly out into space. Okay.
Wow.
Because there's magnetic fields holding it down, but there's also magnetic fields under it pushing it up. So if the ones that are holding it down release, then that prominence can erupt into space, and then we also can get a coronal mass ejection or a CME from that.
Okay, so let me stop you. So is this prominence that we're seeing, this kind of purplish loop that is flying out there in the midst of that lighter blue fan, is that associated with that sunspot?
It's actually not. So this is interesting because that's from back behind the sun. So we're actually seeing an eruption that's happening just around the sun. We call that the backside or the far side. So now, is it related? Maybe, because sometimes, and we actually think that this may be the case for one of these events, excuse me, if there's a flare, a flare is a release of magnetic energy, and those magnetic fields get disturbed. So sometimes when a flare happens, that can disturb the prominence and cause it to erupt. So could they be related? Maybe. It's kind of hard to see right now because we can't see around. But you'll actually notice if you look on the disk, okay, so right down towards the bottom, you see the blue patches, and then there's kind of a long structure in between them. Okay, that's actually a filament. Now, a filament is a prominence. They're the same thing. It's just that when you look at them on the solar disk, they're cooler or darker than the material around them. And so that's why scientists at one time thought they were different, but they're the same thing. It's a matter of perspective. But
Wow.
you'll actually notice it's very hard to see here. And actually, the other images that Raul provided may show it a little bit better. But that filament erupts. And actually, looking at the data today, I think, and I've seen some other observers, some other analysts think that there's a flare that happens right before it, and maybe that flare is actually what disturbed the magnetic field and caused that filament to erupt.
Wow. Let's move to the next image because
Yeah.
maybe we can see the same thing
Okay, so
but differently.
here you're seeing. So you know what? I actually may take back what I said. I think I was incorrect. I actually think no, that loop is different. Okay, so I was trying to make sure that loop we're seeing. Can you go back to the previous one real quick? Let's just go back for a sec.
Yeah, both of these images are from
To earlier
today,
today.
I think.
You know,
Yep,
actually,
today.
I think that this is I'm mistaken. So go back to the reddish one. So you'll see that you can see the filament, the one I was talking about right there, the brighter structure, the darker
Right.
structure. You see that erupt, and you can see this little loop structure come out of it. So I actually think they're connected to each other. So it's
Oh,
not a back-sided filament eruption. This makes it a little bit clearer that it's actually the one that's happening below it.
and
And
that's
what
why
you'll
you guys are looking at these in different wavelengths,
That's right.
right?
That's right. And you'll
Yeah.
notice there's a brightening right before that structure happens. That brightening is a flare.
Wow.
So that's why we think that those two events are related to each other, that the flare happened and then that disrupted the magnetic fields holding that filament down, and then boom, it just flew out into space.
Yeah. So there was a flare. It's somehow connected to this filament on the surface of the sun. And when the flare happened, the filament was released
Yes.
basically into space.
Yes.
And it was released, it didn't just fall back down to the sun, but this one actually went outward from the sun and became a coronal mass ejection. Is that right?
Correct.
Okay.
Correct. And
Okay.
this one is largely not directed towards us. However, coronal mass ejections are very big and they spread out very quickly. So it's currently um, being analyzed to see if that one actually has a component that may, in fact, reach us here on Earth.
It's so interesting to me, and I'm going to move to the next slide because this is a very famous image that many in our audience may already have seen. So this is an image from, I believe this is from 2010. So close to the
Yes,
peak of the last solar cycle. So we're at
right.
the peak of solar cycle 25. This one is from around the peak of
Hmm.
solar cycle 24. And you can see this approximate size of Earth in contrast to this big loop or prominence.
Right. And this is actually from the Solar Dynamics Observatory, which is the other imagery that you saw. But this is, Solar Dynamics Observatory was launched in 2010. So this is actually a relatively new image at the time. But the cool thing is that, they've put a little image of the Earth at the right scale to give you an idea of just how big these things are. They're
Yeah.
just humongous.
So, I mean, these prominences can be like 100 Earth diameters,
Oh
correct?
yeah, and
They're just
easily,
huge.
easily.
It's so strange to think about the sun, our star, 8 light minutes away, 93 million light or 93 million miles away. And, it's just out there doing its crazy thing. And we didn't know much about it until spacecraft started studying it. I mean, we could see sunspots and we could see different things, but we couldn't see anything like this, could we?
No, we really couldn't because we
I'm going
could
to move to the next slide because it's from 1946, and
right.
this was
So
a
now we
very
could,
famous
yeah. So
photo.
this is actually a very famous image. So this is what we could see from the ground. So this is what's called H alpha. So this is a particular wavelength of light that comes from hydrogen. That's what the H stands for. And it is in fact reddish. Okay, so if you're an amateur astronomer, you can buy filters, for example, to look in H alpha. And this came from the High Altitude Observatory, or HAO, which is in Colorado. And this, people have called it the granddaddy prominence. This is one of the largest prominences ever recorded, and with just amazing structure. And this was the one of the things that's really cool about this, and we can see this in the images today, but these prominences, as I mentioned, they're solar material and they're wrapped up in magnetic fields, and so it's almost like a bundle of twine or something. And so when they leave the sun, they unravel. The magnetic fields are unraveling. Now, magnetic fields themselves are invisible, but you're seeing the material following the magnetic fields. And if you look at this, it kind of looks like yarn wrapped up or something, and
It
so
does.
you are in fact indirectly seeing some of these effects of the magnetic field, which I think is really cool that you can do that. And we do that today still.
It looks like a skein of yarn that somebody just pulled into a curved shape, and you can see that wrapping around the whole. And look how much of the sun it takes up. I mean, that's a huge portion of the sun's surface there.
Well, yeah, if you stretch that out end to end, it's actually on the scale of the diameter of the sun, and that's not uncommon that we see prominences that are that big. Now, this one is really kind of neat because also the sun was much more active back in the 40s, 50s, and 60s than it is today. I mean, we're seeing the sun active right now. We are at the peak of the period we call solar maximum, which is a couple of years' time. But when we look at the sunspots over time, depending on how high that peak is, that gives you an indication of how strong the solar cycle is. And the solar cycles back then were significantly larger than they are today. So there was a lot of really large solar activity that happened basically before or right at the beginning of the space age.
Oh, wow. How cool. Yeah, because 1957 would have been Sputnik.
That's right.
Yeah. So very cool. So relatively mild week for flaring, but an active, very active week this week for solar prominences.
That's right. We've seen lots of prominences and filaments erupting, and that's part of what happens during solar activity. Is you also see lots of filament activity, and they've been the showcase this week.
That's right. And of course, the sun doesn't know that we're having days and weeks here. Doesn't know and doesn't care. So it's just doing its solar maximum thing there, not caring about our days and weeks. And here we are at EarthSky. We have an update on the sun every day, and we're always saying, in the past 24 hours, the sun did this or that, but that 24-hour period is not tied to any kind of anything on the sun.
It's very arbitrary. We just picked it.
Yeah. Well, I mean, I guess there was a reason. Well, we won't go into that.
Yeah.
Yeah, that division into 24. I have to look into that. Okay, so let us move on. I just wanted to say to everyone that this is a big thing for us every year. The 2025 lunar calendars are here, and you can see this is a picture of, we just opened the box, and this thing is lying on a pallet, outside of somebody's house. And these lunar calendars are for sale at the EarthSky store. And I think I can pop up the address of the EarthSky store. There it is.
They're super cool.
They are beautiful calendars.
Mhm.
They're big, long, horizontal, not horizontal, vertical calendars that are just, I'll show it one more time. So earthskystore.org, come and buy your 2025 lunar calendar from us, and they make incredibly great Christmas gifts. So let's go back to this.
This is such a cool image. I want to learn how to make one myself.
I don't know if anybody, I would have to go to, let me see if I can jump on the chat here and see if, nope, I don't see any messages from anybody taking a guess as to why the Southern Hemisphere has had more sunspots in the month of October 2024. So Alex, what's going on here?
Well, I have an answer, and it's because the northern and southern hemispheres reach their peak sometimes, not every solar cycle, but clearly for this one, at different times.
Wow.
And in fact, the north had already reached its peak months ago. And this is very, very interesting because if you go back and look at the plots of the number of sunspots over time, okay, and you look at previous cycles, including our own, you will notice some of those have not one big peak, but two peaks. And that is what is happening here. We're seeing that the peak, which happened, we think the peak for, the Southern Hemisphere happened really last month or the month before. That is, we're seeing the fact that they don't happen in sync with each other.
And so wait, did you say that the Northern Hemisphere had its peak earlier, or is it still to come?
The Northern Hemisphere has already had its peak, yes.
Okay. And so when did it have its peak?
It happened earlier this year. I don't know the exact month. I'll find out for you.
Oh, I didn't realize that. I mean, when I
Yeah.
first heard that the Northern and Southern Hemisphere peaked at different times, I thought that my impression was that in one part of the solar cycle, or maybe I thought in one solar cycle that the Southern Hemisphere had all the spots, and in the next solar cycle, the Northern Hemisphere had all the spots, but that's wrong. It's within a single solar cycle, there's a double peak.
And that's actually one of the reasons that defining when the peak of solar maximum is not so, it's not so easy to define that, because you get a peak in one and then you get a peak in the other one. So it's really more of a period. Now you could smooth over that and sort of get a general idea of when the peak is between the two of them, but they're not the same. But one of the things that's important about that is that this tells us something about the cycle itself, because looking at past ones, the stronger, larger cycles tend to have single peaks, and the smaller cycles tend to have more often have the double peaks. So
I wonder why.
That's a really good question. I don't know. That's something that people are studying and trying to understand, but that is what's happening, is stuff that's happening deep inside the sun. The process called the solar dynamo, which is very similar to the process that creates Earth's magnetic field. That's happening inside the sun. That has to do with rotation. It also has to do with the fact that the sun is not a solid object, and it rotates faster at the equator than, closer to the poles. But that process is very complicated. It's very difficult. The physics to understand that process is extremely complex. And so we don't fully understand that. Just like we don't understand exactly why is it 11 years for our star. Other stars have different average solar cycle lengths. You know, some are 9 or 10. You know, we don't have an answer for that yet because we don't fully have a model that truly describes the details of the physics that's happening.
Yeah, and if you took all those sun observing spacecraft that we have and you put them around another star, I'm willing to bet that it wouldn't be the same. I mean, there'd be similarities, of course, and there'd be basic physics that they had in common. But uh-oh, did we lose Alex?
Did you lose me?
Yeah, we can't. I can't see you from here. I don't know if you're visible to the YouTube audience
can you
or
hear
not.
me?
I can hear you.
Okay, yeah, I don't know what happened on my picture just went away. I didn't see anything happen on my end, so
Yeah. But
okay.
to finish my thought, I just wanted to say that don't you think it's very likely that in the same way that all people are different and all cats are different and all snowflakes are different, and don't you think it's likely that all stars are like individuals?
Absolutely, absolutely. There are certainly stars like our sun that are very similar, but you know, none of them are exactly the same size. None of them have exactly the same composition. Um, so that means that the really detailed stuff that drives a lot of the physics, which is very hard to get a handle on, is slightly different. And then that means that things are slightly different. The other thing is um, this process is chaotic. So I won't go into the details, but when you have a chaotic process, tiny little changes make things evolve in very different ways. So exactly, all these stars will have similarities. Some could be almost like, but they're all still unique.
That's the most amazing thing to me about nature. It is so much. There's
Yes.
just it's so much. Okay. Alex, thank you for joining us. We're sorry we can't see you, but I'm glad we can still hear you.
Good. Well, I'm glad you can hear me and I can hear you too.
And we really appreciate you joining us today. That is our Sun News of the Week for this week. And thank you, everyone who's watching, for joining us. We'll be back on Monday when we'll be speaking with Stacy McGaw of Case Western Reserve University about the fact that current theories of the universe don't match our observations of what's happening in the early universe. So do cosmological theories need a rethink? Join us on Monday for a discussion. One Earth, one sky, EarthSky.